Good morning. We are continuing our discussion about the inorganic membrane formation and the characterizations in this chapter. So we can make the zeolite membrane, and zeolite, as we have already looked at in this slide, is zeolite comes from the Greek word meaning that it's a boiling stone. Okay, so that means that you have a very porous nature in this rock, so that it's called a porous rock. And the zeolite could be formed where the volcanic rock of the specific chemicals coming from this position, and it's immersed in water, so as to there is a leak. There is a water vapor coming from this component. It's called the zeolite, and they can mimic this zeolite. And zeolite could be widely used in the chemical reaction engineering courses, and zeolite was manufactured as a catalyst, in fact. And we already talked about these zeolite structures, sometimes called the Fauser-site framework type, and the FAU or Fauser type unit is called this zeolite A. And zeolite A to zeolite Z, there are many types of zeolite, in fact, and it's composed of a silica and oxygen, and you form the frameworks, so you have a lot of pore structures in this case. Of course, this is the crystalline material, and because of this, the very ordered structure, you see a lot of the pores. So through those pores, the water vapor or water is coming out, the hot waters, in fact, as you have seen the boiling stones. And in many cases, you have the very ordered structure in the three-dimensional channels. And recently, you can form this structure with the size of around 3 to 4 angstroms, whereas about 10 years ago, they found that they can make this framework with the 7 to 8 Armstrong level, whereas it's coming down to about the 3 to 4 Armstrong level right now, so that they can separate the gases even. But of course, the price of this, the zeolite membrane is very expensive compared with the polymer membrane. But anyway, one of the beauty of this zeolite is that they can have a very well-defined molecular dimension of those pores. So through those very well-defined pores, they have a very good separation and the selectivity. But still, the economics might be an issue in this case. Zeolite membrane, although you can make the zeolite powders, okay? Zeolite powders can be utilized as a catalyst, as I mentioned, but zeolite membrane in the fleshy form or the tubular form is a different story, okay? Because you have to make a very well-defined and flexible tubes or flesh sheets with the flexibility, and that's very difficult to make this zeolite membrane in a larger scale. If you're making just a flesh sheet form in A4 size or less than smaller than A4 size, yes, you can make the measurement. You can say that the zeolite membrane has a very good property, very high performance, stuff like that. But the real application is really a different story. But these days, I think the technology has been advancing to make pilot scale units with a flesh sheet form. What they call is a plate and frame type of modules. Plate and frame type of modules in a vacuum, and zeolite membrane right now could be utilized to the evaporation membrane systems, where you pull the water from your aqueous system so that you can concentrate your aqueous, your organic solutions, or you can pull the organic matters, organic compounds out of your aqueous solution, so that you can concentrate your organics out of those hydrophobic or hydrophilic gel-like membranes. And that's been commercialized in Japan, and it's been utilized in biofuel applications and biodiesel the productions in Brazil. Anyway, other than that evaporation units, there is no commercial geolite membrane in the world. But anyway, you can prepare the geolytic membrane in such a way that you have to first treat with the support, and then you can make the you can synthesize your geolite on top of your support. What they call is a seeding. Okay, you can seed your geolites just like a nuclei and growth mechanism, and then grow the crystals between the interface of the two phases, and etching, seeding, electrotrapping, pressurized joule gauge, binding, electrical, blah, blah. You have many steps to make these geolytic membranes, and it's very tedious, very difficult to make the final. You have come up with many stages, and that bothers the making your large scale geolytic membranes. Okay, and then that's not the end. That you have to impregnate your support and eliminate your small defects and so on. So you have to micro purge your silicones and so on. Anyway, starting from your support, come up with a final membrane without any defects will cost a lot of money, will take a lot of time. Therefore, the economics is not really feasible at this stage in industrial application of these geolytic membranes. Anyway, you come up with ceramic hollow fiber, which could be, which is not the geolite, but could be the alpha alumina or coated with gamma alumina, and you can start from the alumina. Although alumina tube is also expensive, we bought this alumina tube maybe about few hundred dollars per tube. Okay, it costed too much for us. Then you can start from your hollow fiber or the tubular form of your alumina, and you can come up with the many steps and come up with the geolytic membrane, sodium NaA type of geolytic membrane on top of the ceramic hollow fiber membrane. It's just one example of this geolytic membranes. In our carbon capture project, we have two geolite membrane projects going on in KCR's project, and one is about the pure all silica geolite membrane from Professor Choi at the Korea University, and he's doing all silica geolite which repels the water, so that the repelling property of this silica will be beneficial to the carbon capture project, because most of this geolite membrane, as we have seen, the well-defined pore could be blocked by the presence of water. Okay? Water will block the pore, so that final property will be much more reduced due to the presence of this water. So what he's doing is that if we can coat those all silica very thin layer on top of this geolytic membrane, then we can improve the performance of this geolytic membrane. And the other project, second project, is making the geolytic hollow fiber system. Geolytic hollow fiber system could be fabricated by blending geolite particles with the polymer, okay, and fabricate the hollow fiber system just like what we have done here in the laboratory. And you fabricate the hollow fiber from the blend of PVP, polyvinyl pyridone, with the geolites. And that way you can easily fabricate your geolite blend, polymer blend membrane. And the second step will be the removing this polymer at high temperature, such as I think it's of 600 or 700 degrees C, so that you can bond this polymer out and come up with a flexible, relatively flexible, I would say. It's not like a polymer, but it's a relatively flexible remaining framework of the geolites. Okay? But this geolite has a lot of defects, although you can fabricate those hollow fiber in a very easy way. But still, the mechanical strength is good, but the flux is pretty high, but selectivity might be low, and water will be the detrimental to this geolytic membrane. Therefore, these two technologies can be combined together to coat those hollow fiber, geolytic hollow fiber, with the all silica geolites, so that they can utilize this membrane in CO2 capture systems. But they have not done yet. I know that there is a Professor Jung at the Texas A&M who could, I didn't know exactly what he will be doing, but we invited him on May 27, the Tuesday. So I think he will talk about his key technology on the mass production of the very thin layer of this geolite on top of the hollow fiber systems. So I was told that his technology could be applied to any polymeric systems, not limited to the geolite membrane, but could be applied to the porous hollow fiber systems. So if you can have a polymeric hollow fiber coated with the geolites, very thin layer of geolites, I think we can make the very nice the separation membrane systems in combination with those polymer and inorganics. Anyway, we'll see what happens. And next, topic that we have already talked about is the palladium membrane. Okay, palladium membrane could be classified as ITM, ion transporting membrane, because the palladium, through this palladium membrane, which is metallic membrane, hydrogen atoms, hydrogen molecules cannot penetrate through, but the only mechanism of this hydrogen production is through this ion transporting mechanisms. Because water, you have the hydrogen molecule with the CO2 molecule, and hydrogen is much smaller than the carbon dioxide and water, so that the hydrogen molecule can be ionized on top of the palladium interface, and these ions, protons for example, could be transported through this palladium metallic layer and will be again associated on the bottom of this palladium membrane to become molecules, so that so through this mechanism you have a separation of the hydrogen only, not carbon dioxide or water, through this palladium membrane. Of course, you have to have a very thin layer of palladium. The thickness of this palladium will determine the economics of your membrane, because the thick membrane palladium, of course, will be very expensive. So thinner the better. Thinner and the permeable, it will be the ultimate goal of your palladium membrane production, of course. And there are a large number of groups, as I told you already, particularly from Professor Ma at Worcester Polytech, is the pioneer in the palladium membrane. Ted Oyama from Virginia Tech, and Professor Tsuru and Kimura and University of Tokyo will be the leading in this area as well. We have a Professor Dr. Park at the KIR, is Energy Research Institute in Daejeon. They're all also working on the palladium, and also palladium alloy membranes as well. They can purify this hydrogen for the energy as an energy sources for the fuel cell, and I think we have already done this. Purification and the separation of this hydrogen is very important for the future, because you knew that the PMFC, polymer electrolyte membrane system, could be applied to the automobile systems, but not only on the automobiles, they can utilize this hydrogen as a fuel for the home, the generation system, the electrical generation system at home, because if you're isolated in some areas, it's very difficult to get the electricity. But if you have fuel generation from your gas, okay, then such as natural gas or butane gas, you can generate the hydrogen from PMFC and get the electricity out of this the PMFC system at high temperature. Could be one way of getting the electricity as well. Of course, in perhaps 10 years or 20 years later, we can get this hydrogen from water, but at this point, it's not possible because of the technology gap. But in the future, of course, we need to get the hydrogen from the water, so that we can easily supply this energy from the natural resources. Then I think the automobile will be fueled with water, okay, and get the electricity from the PMFC, and you have a large number of vehicles from this PMFC system as well. Now we have an electrical vehicle, right? Electrical vehicle, but electrical vehicle needs the electricity and should need the charging system, okay, charging and discharging. Although this electrical vehicle could be regarded as a clean car, but it's not clean because we have already spent some money and also generate the CO2 when you generate the electricity, okay, from the coal-fired power plant or the natural gas fired power plants. Because even in Korea, we have about 55% of our electricity is produced by the coal-fired power plant and gas-fired power plants, and about 30 to 33% is from nuclear, right? So if you have electricity, then you already paid for your the environment when you use your electricity anyway. So the electrical vehicle is not 100% clean, but we have to already paid the cost for environments anyway. Next topic that we will talk about is a liquid membrane. Okay, a liquid membrane is the membrane that is in the mobile phases. Mobile phases. We have talked about already whether you are talking about the polymer membrane or a metallic membrane or ceramic membrane. Those were in the form of solid phases, whereas a liquid membrane is called the liquid phase or mobile phases. And liquid membranes are pretty important in facilitated transport or coupled transport, which utilizes the carriers to transport of the certain components. And this topic is very well known, and we have in our department Professor Yong-Soo Kang is a pioneer in the facilitated transport area. But so far we do not have a commercial scale facilitated transport membrane, and that's one of the issues which I will tell you in a minute. Okay? But liquid membranes can be utilized for the selective removal of the heavy metal ions or selective organic components from the industrial effluents, because in industry, the particular chemical industry, we have a lot of wastewaters, we have a lot of wastes containing the metallic components, and those metallic components should be recovered in some way, in such a way they should be recovered. And for example, if we are using, well, in your electronic systems, we have a lot of precious metals. And we use a lot of, in fabricating your semiconductor systems, we use palladium, we use a lot of coppers, a lot of other precious metals, and those precious metals cannot be discarded in the nature, but we should recover it to reuse it for the next generation electronics. So in recovering those, the heavy metals or selective removal of those components, we need a very efficient way of separations. Okay? And we can see some of those liquid membrane systems in some way. Or we can utilize the solid phase as a support. For example, hollow fiber system as a support, and liquid phase as a mobile phase, and that's called the SLM, solid liquid membrane systems, not just the liquid membrane only. And we have a lot of a large number of the, and also the variety of membrane, liquid membrane in the world as well. So this is one of the example. This is the supported liquid membrane system that I have just talked about. We have a porous support. We have porous support, and we have two phases, aqueous phases. And this porous support is filled with the liquid membrane with the mobile, with the separation capability. And of course, if you have the thicker membrane support, then you have a detrimental effect for your permeation, so that the permeability will be much lower. If you have a too thin the layer of the support and liquid membrane, then you have a trouble in the mechanical support. So you should have a very decent the thickness of the membranes. You can make a flat sheet type, or you can make a hollow fiber systems. Okay, in both phases, you will be able to separate the systems. Okay. Usually, they use hydrophobic membrane in the hydrophobic liquids. Okay, so the chemical stability of this membrane is very important. The typical hydrophobic membrane will be PTFE, tetrafluoropolyethylene, PTFE, or polyethylene, and you can make a porous membrane by stretching and sintering. And through those pores, liquid active ingredients were filled, and so that those carrier will be acting as separating layers. Much more complex system will be the emulsion type liquid membrane, ELM. And emulsion liquid membrane is the one that you have, if you have a stripping solution, which will be removed out, then you put the liquid membrane phase, which contains surfactants and distributing solutions, so that you can mix this together to remove the oil systems. And we have a lot of these SLM and ELM manuscripts submitted to JMS. I think it's about maybe 30 to 40 manuscripts handled by myself only. And recently, I think we are only accepting this SLM because SLM has a solid membrane, the substrate, whereas emergent type liquid membrane is the one that you do not have any support. Okay? Of course, you have a transfer property, but it's very difficult to get we cannot say that this is a membrane. Okay? So membrane terminology could be applied the one that contains a solid membrane. Okay? If you have only 100% liquid membrane, we do not publish the paper. But rather, we recommend them to submit it to separation and purification technology or separation science and technology and so on. And next topic will be the ion exchange membranes. Okay? Ion exchange membranes contains ions, of course. Okay? We have fixed ions. If you have fixed ions in the negative form, we call this as not an ionic exchange membrane, but we call this as a cation exchange membrane. Okay. Now, again, I will repeat. Okay. I will repeat. If you have a fixed negative ion in your support, in your base, we call this as a cation exchange membrane because you exchange cations rather than anions. Anions are remaining. So the exchange membrane is the one that you exchange the counter ions. Okay? Counter ion is exchanged. So this is different from what we call 용어를 까먹었네. Sorry about I think I forgot what I'm going to say, but anyway, ion exchange membrane is the one that you exchange ions. Okay, it's not fixed ions, but it's a counter ion. Counter ion is exchanged through this IEC membrane, and so when your counter ion, in this case cation, is exchanged, we call this as a cation exchange membrane, and vice versa. Okay? And anion exchange membrane, cation exchange membrane has the fixed anions, such as sulfonic acid or carboxylic acid, and permit the transfer of cations only, whereas anion exchange membrane has a fixed cations, so you can an AM only allows the transfer of the anions. Okay? So we have a CEM in abbreviation, and AEM. AEM contains such as the potassium, such as the quaternary ammonium salt, N plus ions, or the imidazole ions or ion liquids. Those were classified as AM, and CM is the one that contains negatively charged anion containing membranes. We need the selectivity in this IEC membrane. We need the pump selectivity of the membrane with a high permeability for counter ions and impermeable to co-ions, of course. So we need the selectivity. We need to select only the counter ions rather than the co-ions if you contain both of those ions, of course. we need to know about the electrical resistance. Electrical resistance is defined as the permeability of an ion exchange membrane for counter ions that should be as high as possible. So permeability of the counter ions should be as high as possible. And of course, the mechanical property and the stability is one of the issue in this case as well, because we are dealing with very high pH and low pH, those cases. But the selectivity and the resistivity is a trade-off relationship. So if you have a high permeability, the membrane, then the electrical resistivity should be low, and vice versa. So we need to, we need to compensate. We need to, improve both of those, selectivity as well as the electrical resistivity, and the stability as well. Again, the fixed anion for the cation exchange membrane, CM, is sulfonic acid, carboxylic acid, phosphoric acid, stuff like that. And AM has ammonium salts or phosphonium salts, and so on. We can have a homogeneity or heterogeneity in IEM. The heterogeneous membrane in preparation is much easier than the homogeneous membrane. However, the heterogeneous membrane with the high conductivity of the ion exchange resin will be around 50 to about 70%. This means that we have a lot of the swelling property, and if you have a high swelling property, then you have the mechanical stability might be very low. Okay? So we need to compensate between the swelling and the mechanical property in this case. I can show you some examples of making the IEM. In this case, we have CM containing sulfonic acid groups from styrenes. Okay? The styrene can be copolymerized with divinyl benzene. The styrene has the bifunctional groups, because the one vinyl group is regarded as a bifunctional, and if you have a two bifunctional group in one monomers, this is regarded as a tetrafunctional. So bifunctional group will form the polymer, linear polymer, whereas bifunctional group will act as a crosslinker. Okay? So the DVB will be acting as a crosslinking system. So you can make the crosslinked form of your films or form of your powders. So if you can make a powder, then this will be the main ingredient of your the liquid chromatographic column components. You can fill this DVB and the polystyrene as a particle, as a porous particle in your chromatographic columns to separate something. Right? Particularly the liquid chromatography or high pressure liquid chromatography. If you sulfonate them, you can make a sulfonated polystyrene at the para position of the vinyl group, because this is the para position, para functional, the ortho and para functional monomer positions. So if you control the sulfonation degree, then you will be able to make a certain degree of sulfonation of this the polystyrene systems. And this is, although I have written here as SO3H, if you treat this polymer in sodium hydroxide, because it's acidic, if you treat this polymer in the sodium hydroxide, then this will be charged. So you have a minus sulfonated one, and instead of proton, the sodium Na plus will be attached to here. Okay? So you have a ion exchange capacity of these polymeric systems. Second example is a polystyrene, but instead of just a polystyrenic monomer, you can make the polymerization with the chlorinated the material, so that you have your para position 1 will be substituted with the methyl chloride, and if you make a quaternary ammonium salts, then you come up with the quaternary ammonium terminated one with as a fixed ion, and chloride will be the co-ion or the counter ions. So because we have a mobile phase is anion, this is called the anion exchange membrane. Okay, this way you can make the AEM membrane, and of course degree of how many moles of your para position styrene could be substituted will determine your degree of amination of your final polymeric structure. Not only just the sulfonation of a polystyrene, you can make a polyether ether ketone, and then post-sulfonate to make the sulfonated polyether ether ketone. But these days, I think we can make the sulfonated monomer, so that you can come up with a sulfonated peak, S-peak, so-called S-peak, sulfonated peak, could be manufactured in an efficient way because of the availability of your monomer containing sulfonic acids. About 20, 30 years ago, this was not possible to make a good yield, so that only post-sulfonation was very popular, but the post-sulfonation has very difficult to make it in a reproducible way, so that these days sulfonated monomers could be utilized to make the right determination of your sulfonic acid, degree of sulfonations. Okay, so we make this the aromatic polymer pretty efficient way. You can also make the diazo bicyclic components here in this case, this will be cottonized. This was first used as a crosslinker and cottonized later on to make AEM, of course, with a very high efficiency. And these are the examples of the manufacturing of the AEMs of the polyether ether sulfones. In the literatures, you will be able to find a lot of other examples, of course. You can make the benzimidazolium type of the polymers with the backbone of polysulfones, polyketones, polysulfones, polybenzimidazoles, and so on. And even in our laboratory, we are making these types of polymers as well. Typical ion exchange membrane containing sulfonic acid group is Nafion. This Nafion was manufactured by DuPont in 1970s, of course 60s and 70s, because of the space program in the United States. The NASA needs the energy from the space, from the space the shuttle, because they need to regenerate their urines. Okay, you need water in the space, but of course you can carry your water in some points, but you have to reuse your urines, or you can generate electricity through this fuel cell, okay, by the fuel cell, of course, at the time. And the Nafion was manufactured and first manufactured by DuPont for that purpose. Okay. What it is that you need, and this is a very unique membrane. You have tetrafluoroethylene units, of course, tetrafluoroethylene units in the backbone. Okay, backbone. So you have very stable, CF2 units, and at the end of your chain, you have a side chain composed of sulfonic acid group here in this case, and you can control this length of these side chains. Okay, side chains, and typically, although there are some numbers, typically you have a certain degree of the chain length in this case. Now, when you have this structure with the sulfonic acid group here in the X, the CF2 group is very hydrophobic in chemical nature, whereas the sulfonic acid group is hydrophilic. So you should have a phase separation between the phobic and philic property in the same polymeric units. And it's not very easy to manufacture this Nafion membrane, but anyway, they optimize this Nafion membrane in the 60s and 70s, and I saw the picture of their manufacturing in the literatures of DuPont that they have done a lot of efforts in making these unique membranes. Because of the success of PTFE membrane backbone from the 50s and 60s by DuPont chemists and chemical engineers, they tried to make a water soluble, and they tried to make a water absorbable polymer made of fluorine backbones. Okay? So this has a very excellent chemical stability. It has ion exchange capacity because of the presence of these sulfonic acid groups. And it can withstand the very aggressive conditions like low pH and high pH levels. And this membrane, although it was developed for the military purpose and space purpose, it could be utilized to separate the ions, separate particularly the cations in the chloralkali industry. Okay? Chloralkali industry uses a lot of ion exchange membranes. For example, if you have a sodium chloride in the seawater, they need to separate the sodium chloride, and they would like to use this chlorine Cl2 in their chemical industry. Okay? Now chlorine, first of all, is the main component of your seawater. So instead of using other the natural resources, the seawater is the main source of your chlorine. Okay? So if you can separate the sodium and chloride, they can obtain the chlorine from the sea and can supply this chlorine Cl2 into the chemical industry, which is located nearby the sea, okay, and can make the other chemicals. So Nafion has already been used in chloralkali industry to make the chlorine in this case. Of course, Nafion has been very expensive. It's about right now. I think it's about $300 to $400 per square meter, but it's been more than $1,000 about 10 years ago. Of course, Nafion was not the only solution for chloralkali process, but as you have seen, the polystyrene membrane, the sulfonated polystyrene, and sulfonated other hydrocarbon membrane has already been commercialized by the Japanese producer and the Dow Chemical, European companies, and even in the Hanwha, Hankook-Hwayak, the companies using or the manufacturing those ion exchange membranes and ion exchange resins. Okay? But Nafion was a very novel polymer, but expensive, so that although it could be utilized in a chlor-alkali process, the chip, the polystyrene-based ion exchange membrane has long been used in those industries. Okay, so those were the membrane of the choice, and I think I will briefly mention to you about what kind of materials have been employed in membrane processes. Well, we have a hydrophilic membrane and hydrophobic membranes. Hydrophobic membranes are the ones that does not have the large capability of the forming the hydrogen bonds with the water, or hydrophilic membranes are the ones that contains the philicity. Okay, so phenyl polymer, polyamides, polyacrylonitrile, and PVA are the hydrophilic membrane, classified as hydrophilic membranes, whereas these were classified as hydrophobic membranes. Okay. Usually the typical composite, what they call is a evaporation membrane, is the one that has a PDMS coating. PDMS is the silicon rubber coating of the membrane on top of the polyacrylonitriles, and the organomethyl silane cross-linked membrane contains some of the hydrophobic, the oligomeric siloxane coated membrane on top of the polyethylenes, and the polyester fabric or the nonwoven fabric could be utilized as a support. In terms of evaporation performance, we have selectivity or separation factor, and the permeance or the flux, and you have a great number of the larger the better. Okay, flux is, and as well as the separation factors. In the first column, we can see the binary mixture of the organics. For example, you have a cyclohexane and cyclohexanone, normal propanol and heptane, and so on. And in many cases, you have a mixture of organic and organics. In evaporation processes, this process has been known for the last 50, 60 years, but the first industry was found in 1981, I believe, by the invention of the people in Germany, where GKSS manufactured the polyvinyl alcohol membrane. Polyvinyl alcohol, very thin layer of the polyvinyl alcohol was cross-linked on top of the polyacrylonitrile PAN-based membrane, and they make flash chip membranes. This flash chip membrane was stacked into the layer by layer, and then was pooled in the vacuum. Okay? When they supply the aqueous ethanol containing about 90% of water and about 10% of ethanol. Okay, 10% of the 90% of ethanol and 10% of the water. Okay, and if you think about the aqueous ethanol, it forms azeotrope at 95.5% weight percent of aqueous ethanol forms azeotrope. Azeotrope means that there is no separation at the azeotropic points. Okay? So unless you add the components such as methanol, the benzene. Okay, if you add benzene, small amount of benzene, then you break the azeotropic points, and then you can continue on the distillation of the ethanol and the water. coming up to about 99.9% of the ethanol. So you see, if you buy your chemical, ethanol, 95% ethanol is very cheap. But if you buy 99.9% of ethanol or 99.99% ethanol, cost will be absolutely different from your 95% ethanol because of the difficulty in separating the azeotrope aqueous ethanol. Okay? So usually when they wanted to break this distillation curve, they have to add benzene and breaking those azeotrope, and further distillation will eventually come with 99.9%. However, there is always a possibility of containing small amount of benzene in your ethanols. If you use ethanol as a biofuel, for example, as a biofuel, then it may contain small amount of benzene, which will be much more harmful for your environment, of course. Therefore, the new process called the evaporation has been highlighted in the 80s, early 80s, which is about 30 years ago. And the people in Germany was spotlighting this polyvinyl alcohol membrane. Polyvinyl alcohol, of course, can attract the water, not ethanol, because of the hydrophilicity of the polyvinyl alcohol membrane, so that you can attract the only water, 10% water. Okay? So that if you have evaporation process of this aqueous ethanol, 9% ethanol solution as a feed at around 100 degrees C, the water vapor will meet this membrane, and the water vapor will be only collected in your vacuum system, and then you can condensate those vacuums, whereas the retentate will be remained as your product, okay? So that you can obtain the very high the separation factors. But in this case, you have organic separations. Organic separation will be very important in the future, okay? In the future, because organic separation is very challenging, and you have a lot of other components. You have a lot of other combination of the organics. So I believe in the future, organic separation using evaporation or organic separation by nanofiltration will be a very important area for membrane industry. But you see, they use different membranes, usually the hydrophilic membranes. As you can see here, most of them are cellulose acetates or naphthiones or PPO with quaternary ammonium salts and so on. So it looks like that they are pulling hydrophilic component rather than hydrophobic components. And you see you have some mixtures of hydrophobic components like hexane, hydrophilic components like methanol and ethanols. However, hydrophilic and hydrophobic term is very relative to each other. So ethanol or methanol in this case is hydrophilic compared with heptane and hexane. But if you're talking about the ethanol and water is much more hydrophilic than the alcohols. So philicity, phobicity are very relative terms, not the absolute terms. Anyway, by using these membranes, you can separate this with a very high flux and high separation factor. Of course, separation factor is determined by the composition, of course. Right? The inorganic membrane can be utilized to separate the methanol with MTBE. MTBE is methyl tertiary butyl ether, and MTBE can be utilized in gasoline, so that it will be it should be added to increase the octane value, and you can separate the organics by using this inorganic membrane as well. For example, the Na-white zeolite membrane has a very high separation factor for methanol and MTBE, and pretty high flux, relatively high flux. This is about 320 grams per square meter per hour with a very high separation factor with a 10% methanol. And I know that this zeolite membrane manufactured by Mitsui Engineering in Japan can be utilized in Brazil to separate the ethanol from water, so that there's a lot of success power plants, industrial plants to separate the ethanols from aqueous solution, from sugar cane, of course. Solvent-resistant polymer membrane, sort of a NF membrane, I would say, or the RO process and UF process needs the membrane with the high solvent resistance. Typically, the solvent-resistant membrane is made of silicon-based membrane, and mainly the polyimide membrane has been known for the nanofiltration membranes, and polyamide imide membrane has been known for a while, and this was manufactured by the Union Carbide, but right now Solvay are manufacturing the Tolon. Polyaramide is of course very highly the chemical resistant, and this was of course made by DuPont. Polysulfone is from Solvay as well. Polyacrylonitrile has been known for a while, and you have many producers of these polyacrylonitriles. And if you take a look at these applications, they can separate the hydrocarbons, they can separate the acids, they can separate the enantiomers, even, and also the hexane recovery and so on. So the organic separation is a hot area in the membrane industry, but it's of course difficult, very difficult, and you have to customize the applications. Other potential solvent-resistant membrane could be PTMSB, PPS, polyphenylene sulfide, PEEK, PBI, and PBA, and so on, and copolymers of those. And of course, polymers could be utilized as a solvent-resistant membrane. Membrane emulsification has been, I think, touched by Professor Drioli, because Professor Drioli's group is very, well studied and very well, known for this membrane emulsification, as well as membrane crystallization and in process intensification areas. So I will just quickly go through. I'm not an expert in this area. And they use a very porous membrane, a hydrophobic membrane. Inorganic material could be zeolites and ceramics. Using this, the inorganic membranes usually, and the porous membrane, they can separate the components. SPG is called the glass membrane. This is a Schrash porous glass membrane. I think it's from glass, named from Japanese. The Schrash, S means Schrash, porous glass membrane. with a porosity of about 50% or 60%, ranging up to about 80%. Okay, and they can separate the many of the membrane emulsions and emulsions, and these were quite well known, the polymeric membrane with a lot of porosity. It's like the emulsion liquid membranes, but you can use this membrane, porous membrane, as a support for membrane emulsifications. So this will be the work as a supported emulsion membrane, I would say. Okay. Okay, so far we have touched about the polymer or an inorganic membrane preparations. Okay? And from now on, we will talk about the membrane characterizations because characterizations of the membranes are, of course, very important as well. I will not touch about the characterization of the polymers and organics, but I will touch about the characterization of the membranes. Okay? Characterization of polymers and characterization of a membrane is a little different because we need to talk about the porosity in membrane characterization. We need to talk about the morphology of the surface, morphology of the cross section. We need to talk about the ion exchange capacity. We need to talk about the surface property. Okay, what about the surface charges and surface, roughness and stuff like that. So we can touch about this membrane characterizations. Membrane characterization is pretty important, I would say, and you can at least detect the porosity, pore size, and so on. And this will be very important for your applications because you knew that outer membrane has a very small pore size, whereas microfiltration needs larger pores. So porosity or pore size will be very important and for your applications. Okay? So in terms of the porous membrane, such as the application like ultrafiltration or microfiltration, we need to at least know about pure water permeability. Okay, when you cast a membrane, first property that you have to see is what about the water permeability of the pure water, okay? Not the salt water, okay, because the salt water could be only applied to characterize the outer membrane performance or NF membrane performance. But if you're talking about the microfiltration membrane, you don't need to know about the permeability of the salt water. So pure water permeability is one very single the characteristic of the membrane that you cast. Pore size, of course, is very important. What about the distribution? What about the molecular weight cutoff? Molecular weight cutoff is very important. So that I will describe what is MWCO. Okay, MWCO is defined as 90% rejection of your molecules. Okay? So if the molecular weight cutoff is 1,000, then means that you can separate the molecules higher than 1,000 of your molecular weight can be separated with 9% probability. Okay, if it's lower than 1,000, then those molecules can pass through. So molecular cutoff is very important to know about the property of your, particularly the ultrafiltration. Other important characteristics are the fidelity, phobicity, whether you have charges, symmetric, asymmetric, could be utilized by knowing the SEM picture of your cross sections. Mechanical property, chemical stability, of course, are the very basic property that we need to characterize in terms of the membranes. So let me describe this difference between the permeability and flux. Okay? Permeability and flux is different because permeability is a property of the membrane itself, whereas a flux is determined by the flux is dependent upon your applied pressure. For the same membrane, if you apply the pressure, then high pressure will induce the high flux. So flux is not dependent upon membrane itself, but could be applied to the applied pressure. So flux is a function of pressure, and it's related with your permeability. We call this as a hydraulic permeability, and dependent, of course, on the viscosity of the liquids. If your viscosity is water, then you can cancel this out. But if you're dealing with the highly viscous solutions, viscosity is inversely related with your flux. Okay, so LP is a hydrodynamic permeability, and delta P is a pressure difference, and JV is the membrane flux. Usually, for the flux, usually microfiltration, the water flux is about the order of several hundred to about several tens of thousands, okay? And ultrafiltration is less than about several hundred, okay? Less than about several hundred is pure water flux. So in order to determine the permeability, what you can do is that you need to put your membrane into your cell and apply the pressure with the water filled on top of the membrane. Okay, if you apply the pressure, pressure could be plotted in the x-axis, and the water that's coming out through the membrane can be measured, so that by knowing the volume or the weight, if it's the water, then it's the same as kilogram. Divide by the membrane area, divide by the time of your measurement, could be plotted, and the slope will be LP divided by eta. If eta is equal to 1, then it's the same as LP. LP is the pure water permeability, hydrodynamic solvent permeability. If you change your solvent from water, then your LP might be different depending on your systems. If you're dealing with the organics, of course you can measure the LP of your solvent. This way, you can measure the pure water permeability or pure solvent permeability. Okay, I think we can restart again about the permeability or characterizations on Friday. Any questions so far? If not, then I think I will see you on Friday. Thank you.